Okay, so today's video is going to be regarding heat exchangers and calculating how much area you need in the heat exchanger or how large the heat exchanger needs to be in order to accommodate or carry out the desired change in temperature that you need for your required fluid. And so the first thing to note is, well, you have different kinds of heat exchangers, right? You have this case is a shell and tube heat exchanger, and the reason why it's called a shell and tube is because you can think of like we have a central pipe going along, right? We have a central pipe that goes through, and we have a certain, let's say that we want to heat up a certain fluid, right? We want to heat up, let's say we want to heat up some ethanol, right? So we have ethanol going from here at a lower temperature. So we can write this as TCN, right? And it's going to get heated up by water. Let's say our fluid going through that's transferring heat from the shell to the tube is going to be water. So we have then water, transferring heat over to the central pipe. And so the ethanol is going to get hotter. And so we have a TC out. The water is going to be initially hot, but because it's transferring heat over to the pipe, it's going to be getting colder. So TH out is going to be less than TH in, and TC out is going to be greater than TC in. And so the reason why it's called a shell and tube is because we have a central tube and we have this water that's going to be kind of enveloping the pipe. And so you can think of it kind of like a shell. All right, perfect. And so when it comes to defining, the fluids, it's important to know which fluid is what. So the process fluid is what we care about. We uh, we care about constraining it because we want the water, or the rather the ethanol in this scenario, right, to come out at a certain temperature. So we already have this as predefined, oftentimes. For a certain reaction, you need the TC out to be specified, and so TC out will be specified, and you'll probably already know what TC in is because you know what temperature the ethanol or the process fluid is coming in at. The other fluid, the water that I was talking about, that would be going through the shell, is called utility fluid. So uh, fluid that is transferring heat. So it could be transferring, but it also could be the opposite, right? It could be absorbing the heat. So um, we don't really always know what's specified, not always specified. So this is something that we're going to need to calculate. So the required temperature gradient, because we're using this to either cool or heat the fluid to a desired temperature. Perfect. And so identifying which fluid is which is the first step in doing these kinds of problems. The second thing you want to know is we want to identify the flow rate. So identify flow rate, the specific heat, so Cp, and desired temperature difference of the process fluid. And the reason why we want this is because it will help us to find the total heat, the load, or the duty of the heat exchanger. This is also called. All right. And then the third step is to specify the type. And when I say type, it's not exactly like the type of heat exchanger, but rather there's two kinds of types of flow that we could be doing. So we could do co-current or countercurrent flow. And there's a difference between the two. So you can imagine that in this case, I have the utility fluid coming in on the other end, where the pipe where the process fluid is flowing out, but it's coming in then, and it comes out closer to the entrance, right? So it's kind of like flowing. If I was to draw the flow, it would kind of be generally. Let me do this in a different color. It would be generally going like in this form, right? in the shell, whereas we have the flow going like this. So it's kind of like opposite directions, right? Because we have the utility fluid going this way, the process fluid going this way. And so this is countercurrent. It's called countercurrent flow. But if we had the opposite, right? If we had, let's say the fluid was going, um, the utility fluid had an opening here, and the outlet was over here. It would be going kind of parallel to the process fluid, and so that would be an example of cocurrent flow. So that kind of flow really matters because there's a difference in the temperature gradient that is going on, which I'll explain later. Um, but we need to specify that type. And then the next thing that we also want to do is, once we specify the type, we also want to know the number of passes. So what does the number of passes mean? Well, in this case, we have only one pass. But sometimes this pipe, when we want to, let's say that we want to maximize surface area, but we have a limited constraint on how big this shell and tube heat exchanger can be. Well, sometimes what people will do is that they'll design heat exchangers that will actually, instead of going straight out, it will actually loop. So it'll go back. So this will actually loop over. And so it might loop like this and have the process fluid coming out after a certain number of passes. So this would be 1, 2, 3 passes. And so the number of passes matters because it basically increases the surface area and allows for more heat transfer to occur. And when we have that, the reason why it's important is because that can affect the calculations by including something called a form factor. And so this is really important. All right. Next, the fourth step is to determine. So this is where we start doing calculations. We determine flow rate, the specific heat, right? We might already know that, or the delta T of the utility fluid. So this is where our equation of Q load. Here, let me do this in a different color. Yeah, purple spot. We'll go with this. So this is where our equation of, we first calculated Q load as, right? We found Q load. That would be equal to the flow rate of the process fluid times the specific heat of the process fluid times delta T, right? So this delta T would be nothing but TC out minus TC in. So we have what Q load is, but we need to figure out what these values are, right? We need to figure out what these values are. And so we have now another equation that will be basically that this is equivalent basically to the change in energy that we're getting from the utility as well, because energy is conserved. And so what we do is we do an energy balance where we say M1, right? So let's consider the process fluid to be 1, to stream 1, CP1, and then we have T out 1 minus T in 1. And that's equivalent as a mass balance to the negative, because when energy leaves, it's negative. So that equals negative M2, which is the flow rate of the utility fluid, times CP2 times T out 2 minus T in 2. And so this is Q load, which we already calculated. This is our known. And what we can do is we can solve for now any one of these variables. We can figure out, okay, well, what's the delta T, the change in the utility fluid, and then what's the flow rate maybe if we already know what one of these is specified as, and etc. So that's the next step. And then what we do based with that is that we identify, right? So step 5, what you want to do is you want to identify, or sometimes you might be asked to calculate, identify the K and H for each surface. So when I say surface, we have the shell and we have the pipe, right? So if I was to draw like the boundaries, the boundary layers, you could see that we have a sort of a convective boundary layer around this pipe on the top and the bottom. And we have conduction going across, right? So what we care about is, okay, well, what is the H in this convective boundary layer, as well as the material of the pipe, right? What is the material of the pipe that allows for maximum conduction across from the utility fluid to the process fluid? If this is made of an insulating material, well, it doesn't matter how hot we make the utility fluid, right? Because then no heat will be able to transfer. Whereas if this was, something like copper, we would get great conduction. And so we would need less heat essentially in our utility fluid at the start. So that matters. Sometimes you might be asked to calculate it, but it's important to basically determine them. The next step, right? The next step is to calculate the overall heat transfer coefficient. So this would be U. Here I'll put UR. And you might remember from our first video that the way to calculate this is U equals 1 over the area, right? Area of the pipe times the sum of all the resistances. Or you could also write this as the Q load divided by area times 1 over delta T overall. But when it comes to a pipe kind of problem, a better way to calculate this would be this. Here, I'll change colors. U of R, right? Since we have the pipe, it would be the radius of the outer, right? Because we have a thickness for that pipe. R inner, here, I'll just write Ri. Hi, right? The convective layer inside that pipe. Because when I was describing this, I only considered the convective layer on the outside, but we have a convective layer on the inside as well within this pipe. So that matters. Plus RO times the sum of ln of RO by Ri divided by Ki plus 1 over HO. All of that to the negative 1. So this would be the way how you would calculate the overall heat transfer coefficient if this was a single pass, basically a single pass shell and tube heat exchanger. Sometimes though, it will be given to you. U will just be given to you. So that simplifies things. But just in case you need to calculate it. And then one of the last few steps we have is to basically calculate the TLM. So the log mean temperature. So calculate TLM. And so you might be asking, okay, what is TLM? Well, is that just the temperature difference in the process fluid and the utility fluid? Well, not quite. Because if we were to look at basically, let's say that we have co-current flow, right? We have co-current flow. If I was to draw like a graph, right? So let's say that this is the z-axis, right? So we have the start of the pipe here, and then we have the end of the pipe at L. What does the temperature profile look like for each fluid, right? So I'll draw the process fluid in red. So P will be red. Here. Process fluid red, and then we'll draw the utility fluid as purple. So the process fluid, right? It's initially, let's say that this is the case that we're heating it up. The process fluid is going to start out at a certain temperature, right? And as we progress along the pipe, it's going to steadily increase, right? Well, what about the utility fluid? Well, the utility fluid is going to start off hot, right? It's going to start off hot. So, by the way, on this axis, this is temperature. So it's going to start off hot, right? and it's going to basically decrease in temperature. So let's say that we start here, and it's going to basically follow this line. So the process fluid is going to approach a higher temperature. The utility fluid is going to approach this lower temperature. But there's actually a constraint here. So because of this behavior, right, we have an equilibrium point where the process fluid can never be hotter than this line, basically, where these two meet. And so this actually constrains the temperature because we don't have a constant temperature difference. If we call this, right, let's call this the delta T, right? This delta T is not constant. As we approach the end of the pipe, we have decreased heat transfer, whereas at the beginning we have large heat transfer. But if we look at the countercurrent example, right? So let's look at countercurrent. It's kind of like like a inverse relationship, where we have the process fluid, right? It still follows the same kind of scheme. So we have the process fluid being cold initially, and it increases to a higher temperature. But we have the utility fluid kind of being the opposite because it's actually hottest at the end, and it's actually lowest at the start. So it kind of follows like this is not straight, but it kind of follows this general trend. And so you can see that we actually have maximized this delta T at every single step of the way. So we've kind of increased the heat transfer that can happen. And so oftentimes this is why you'll see countercurrent flow as being the chosen system. But sometimes co-current flow can be useful if you want to limit the temperature the exchange at a certain if you want to stop it at a certain time. But countercurrent is usually seen as better for the heat transfer. And this is just the drawing if you want to go back to why countercurrent is a little bit different than co-current. Okay. And so this is the reason why we need a log mean temperature, because it's not exactly constant, the delta T. And so the way how you calculate delta T LM is, let me choose dark green. So delta T LM basically equals delta T. So the difference in temperature, remember delta T is not the change in temperature between utility and at the start and utility at the end. This is the change in temperature between the utility and process streams at a certain position. Okay, and so we have delta TL at the end minus the difference in temperature at the start. All of that divided by the ln, so the natural log of delta T at the end divided by delta T at 0. And the good thing about this equation is that this applies for co-current and countercurrent flow. It doesn't matter what kind of type of flow you have going on, this equation will stand for all of that. Okay, perfect. So we can calculate the delta T LM for that. And so now what do we do? The last step is to basically now calculate the size. So we calculate size A total. So this is like the surface area that is required for the heat exchanger. And how do we do that? Well, A total is equivalent to Q load divided by U times delta T LM. So this is the equation that we use. And this is very analogous, you can see, to this equation that we have here. Perfect. And so this is pretty much all you need in order to calculate the size of the heat exchanger. Now, sometimes what will happen is there will be sometimes things like a factor that you're going to need to multiply by, and that's often the case in industry. So oftentimes a multiplier is used because sometimes there's something called fouling where sometimes gunk can build up in these heat exchangers. And so you want to be able to continue that plant regardless of even if there's a little bit of gunk. And so oftentimes there will be a multiplier that this is the minimum required area, right? So you will oftentimes increase that surface area so that in case things gunk up and you have decreased heat transfer, you're still going to achieve the required process fluid requirements. Um, so you might see like a multiplier. Okay. And the last thing I want to touch on is that form factor that I was talking about when it comes to passes. So you might see that, okay, I talked about that we have a single pass system here. Well, what about if there's three passes? How do I calculate for that? Well, for the passes, right? So let me go over here. Actually, let me go over here. We have this, right? So you're going to need for more than one pass, you're going to need a form factor. And how that form factor comes into play is essentially when you're calculating that Q load. Q load is no longer Q load was initially, right, it was not M, it was UA delta T, correct? But now that we have multiple passes, it turns into UA times F delta T. And the way how you calculate this F comes from this graph. So you'll see that we have y, some parameter y on the x-axis. That's calculated by this ratio of the starting temperatures and the ending temperatures of the process and utility streams. And then we have another parameter called z, which has some sort of combination of, again, the temperatures at either end for each stream. And the way how we read this graph is, okay, we have a certain y that we calculated, and these are the different z's. So this is for z equals 4, right? So we have this is z equals 4, this is z equals 2, and all the way down to z equals 0.2. And you can read this graph, well, if let's say that we have a y of 0.5 and we have a z of 1.5, right? So we go here to 0.5, we go here, we go across, right? This is the graph of 1.5. And so we go over and our form factor is 0.8. So then we can plug in 0.8, and this takes into account if we have multiple passes so that we can finally calculate this area. And if we go back to our equation down here, what this means is now we have, instead of this A, we now have an F in the denominator. So if I was to include multiple passes, we would have F down here. But that's the only change. And that's all you need to know, basically, about calculating the area and size of heat exchangers. Just identify the process fluid, its utility fluid, then figure out, what the Q load is, and then figure out if it's co-current versus countercurrent flow, and then the number of passes. The reason for this, the reason why we want to determine if it's countercurrent or co-current is because that can affect the graph that you use, the correction factor. And so then we determine the flow rate, heat, specific heat, or the change in temperature of the utility fluid. We figure out what K and H is. We calculate what the overall heat transfer coefficient is. We figure out what TLM is, and then we can finally calculate the size. And that's all you need to know.